Good afternoon. Good afternoon, everybody. Good afternoon and welcome. Welcome to the Physics Colloquia series. In this series of talks, we bring together world-leading experts to discuss advancements in their fields. Today we have with us Piero Martin. Marco, do you want to introduce?
Sure. Good afternoon, everybody. So it's a pleasure to have Professor Piero Martin from the University of Padova. Piero is a physics professor, but at the moment he is detached as the interdisciplinary center for Beniamino Segre, which is a committee inside the Accademia dei Lincei, an important Italian cultural institution. Piero is involved, has an important role within the project DTT, which probably most of you don't know about, but he's going to tell us what it is. And by the way, the picture which is on the announcement of the seminar is namely a picture of the machine DTT. And he's been working on fusion research for many, many years. So he's going to tell us more or less the picture, the global picture about fusion research and what the perspectives are, what the important projects are, and so on and so forth. So thank you, Piero, for being here, and the floor is yours.
So I stand here so I can also see the slides. Thank you everyone for being here. Thanks Marco, and to all the department and the INFN group here for the invitation, which is of course it has been very nice for me. It's a pleasure to be here. And as Marco said, I will give you an overview on the present status of the research, with a focus of course on Italy, as we are the Italian community. I've agreed with Marco. I've prepared a talk that probably will be on the simple side for the experts, and there are many in the audience. But on the other hand, targets should be accessible to a broad audience. And in this respect, being in a nuclear physics community, I started with this little piece of history, which has to do with one of the starts of fusion as a Pacific enterprise. And this document has been given to me by Steve Cowley, who is now director at Princeton. He's a British scientist. And it's the report about a talk that Enrico Fermi gave in Los Alamos at the dawn of the Manhattan Project. We were, I think, in the summer or fall 1945. At that time, it was already decided that all the physicists, the non-American physicists, had to leave the project. And so the British scientists were asked by their government to take as many notes as possible about the meetings and to give them to the Secret Service in order to gain as more knowledge as possible. And so this is a report about this seminar that Fermi took by Philip Moon, and it's interesting that it's sent to his boss, that was Chadwick, the guy who discovered the neutron in 1932. And basically, in this document, it's contained a proposal by Enrico Fermi about the possibility of using fusion as a source of Pacific energy. So it's a small piece of history, which is also connected. I opened this talk with two historical example, and the second one has very much to do with my own entrance in the field, that sometimes happens for very strange reason, but and this reason has to do with Mrs. Thatcher. Probably a number of you know she was Prime Minister for a number of years in the UK, and in 1985 actually she promoted a bill with some severe cuts in the science budget in the country. And as a result, 1,500 British scientists published this appeal. They self-paid this appeal for the Times, in which they asked the Prime Minister to take back these cuts. but this didn't happen. She proceeded, and one of the things that were cut was a big experiment that was supposed to be built in the UK at Calum, a fusion experiment with the support of the European Commission. And when the UK government informed Europe that they didn't want to make this, Italy asked for the project, and they got it. And this is the experiment where I started, my scientific career, and it's still there in Padova, the reverse field pinch. Well, this experiment should have been based in Calum, but so as I said, sometimes things happen, even if, in a very unexpected way. Anyway, I think that the basic story, the story I'm going to tell you, it's a story about, basically it's about science, of course, but applied in particular to energy. It's rather clear that a large part of the effort that are being done in the world about fusion has to do with the energy application, with the possibility of producing electricity from the nuclear source as a complement to fission. And of course, I'm not going to comment about in details about that, but I think in my personal opinion, it's pretty clear that any energy transition scenario, which relies of course heavily on electricity, will need some fraction of nuclear power, and which means in the now fission, and in the future probably, hopefully also fusion. Anyway, so that's where, that's the main goal of most of the research that is being done about fusion in the world. Well, this is just has been published a few minutes ago. It's on the website of the ANSA, which is one of major newsroom in Italy. You know that the COP29, opened today with the speech of the head of states, head of government. Sorry, it's in Italian, but while I was with Marco this morning, my phone continued to ring because friends, colleagues send me, screenshots. It seems that our Prime Minister spoke about nuclear fusion. I have no idea whether the Pope mentioned delays about fusion or about energy transition. I suspect that it was not relating about fusion. It was not discussing about fusion, but we should see the transcript. Anyway, it's interesting to see that it's very hot news, not only today, but in recent time. One thing that we experience as fusion community, and Marco and the INFN colleagues who are involved in this know pretty well, is that in the last couple of years, fusion has been, more and more noisy, let's put it this way, in the public opinion, which is good, of course, in some respect. As I will say later in the talk, it might be source of some problems. But anyway, one thing that, for example, another example that sort of tells you how much has been talk about fusion is this small excerpt. This is taken by the final declaration of the G7, a meeting that was held in Italy. This year Italy is the president of G7, and there was this this meeting in Puglia, if I forgot the name anyway. And interesting enough, in these 40 pages of final report, you can find it online, there are about 7 lines dedicated to fusion, which is pretty interesting. It's the first time ever that the 7 head of states talk about fusion. The page before, there is a page about nuclear fission, of course, but it's interesting that there is a growing interest. And this is mirrored in a number of communities. A couple of years ago, more or less when everything started, the Biden-Harris administration launched this initiative, which was still called, Developing a Bold Vision for Commercial Fusion Energy. And this, was launched at the White House, so with a pretty large HICO, and has been followed by a number of workshops and activities, which led really a few months ago, I would say in June, to the publication of these documents, which illustrate the present position of the US government on fusion. It's pretty interesting. It's a free reading. You can download it pretty easily. And as you see, it's signed by the US Department of Energy, so it's the official position of the US. And it takes note of an important point that happened in the last, again, 2-3 years, which is the large increase of private capitals in fusion. Since around about, I would say after COVID, maybe, but even less than that, maybe 3 years, we are assisting to a large injection of private capitals into fusion, which doesn't mean companies working to produce components for experiments. That has always been like that. You know, here you have Ansaldo, you have companies based in Genova that historically do it. But I mean companies that want to deliver reactors, that they claim they have concept to produce fusion. And I will comment at the end of my talk about this. But just to give you a figure, there is this website of the Fusion Industry Association, which again is open. So I quote by heart, but I think that in the last 2 years, 2.5 years, around about 7 billion dollars, have been put on the market by private investors in this company. So, how to say, you would call with a social network language, it's a hot topic, you know, the fusion these days. Which again, it's a good point, of course, for us. But it's not necessarily, obviously, a good point. There are some drawbacks that I will mention towards the end. Well, not drawbacks, but things you have to be careful at least about. This plot, this map, summarize the location of the fusion lab at the moment. You see that it's pretty much widespread, except, and also this will be much of a comment at the end of my talk, in Africa and in South America. So it's a pretty broad program with a number of players, and as I said, the number of companies has been really increasing in the last years. Now we have around about 50, 47 or 48. I think it's the right number. Companies that, as I said, are very active in the design, mostly of concepts. It's real machine of in order to deliver fusion, and you know, the fact that has entered into the narrative of prime ministers is pretty interesting again, because, and not only, I mean, I took the example of today because it just appeared on the newspaper a few hours ago, but in general, and Marco's been assisting at, there was a big meeting, a G7 meeting, the first organized in Rome under the auspices of IEA, and he was telling me that really a number of government representatives made a big case about fusion. So, what is this? Because of course these are interesting stories, but we are scientists, and it's always very important not to be excessively distracted by these things, and just to point to the objective. The story of fusion, at least of magnetic fusion, I should say that just to be fair, that my talk it's devoted about magnetic fusion. We have two concepts, you're probably aware. One is the inertial fusion. I mean, the usual process is just to, I know that we are in the physics department, so we don't need to go into these details, but basically the idea is just to fuse light nuclei. And you have two main possibilities. One is to use brute force, I mean, just with laser, to compress pellet and then to ignite them. And this is what is called laser ignition. The main efforts are in the US with the NIF facility, and in France and in the UK. I won't talk about that, basically because I'm not an expert. But I will talk about the tokamak, the magnetic confinement, which is it's called thermonuclear fusion, because basically it used details of energy distribution in a population of hot nuclei in order to provide these nuclei with energy high enough to fuse. Again, just to go back a little bit in history, the father of the tokamak concept were two persons, the Nobel Prize Igor Tamm and the Nobel Prize Andrei Sakharov. Sakharov in particular is probably pretty known, at least with the people that are, you know, my age or older, as a big activist against the Soviet regime. He won the Nobel Prize for Peace, but he was a great physicist too. And interesting enough, he was a Nobel Prize for Peace, I'm sorry, and he was also the person who designed the largest nuclear weapon ever used on the planet. But anyway, he did both. And another thing that he did, again with his mentor Igor Tamm, was the design, the conceptualization of the first tokamak. Basically, the idea is just to use a donut shape like that. You can recognize, oops, sorry. You can recognize here a solenoid. I mean, this is there are just coils that produce, and also the green one are coils that produce a magnetic field. And the idea is that since you have a plasma, you can confine it with a magnetic field, and if you design the magnetic field clever enough, you can keep it in the yellow tube, in the yellow donut, and you can drive a current or launch a beam or launch electromagnetic waves and heat this plasma until you reach the fusion condition. That's the very basic idea of the story. In fact, interesting enough, the first tokamaks were based in Russia, in Moscow, at Kurchatov. This is the T3 tokamak that was in 1969. I see that time is a bit going, so I have no really a lot of time to go into the details, but there are a lot of interesting stories about those times and about the collaboration between the USSR and the USA, even if we were in the middle of the Cold War. But probably the experiment that you've been more familiar about, it's the European jet tokamak that concluded a pretty long career last year. It was still based in Callum, in the United Kingdom, and it was a European experiment, a big tokamak. I don't know whether you can recognize, probably, a person is more or less this height, just to give you a little bit the scale of the thing. It's a big experiment, which has done a very large number of things, a lot of very interesting physics, has been really the workhorse for fusion for many, many years, but has become rather famous because it has been one of the two experiments that used deuterium and tritium. The other one was TFTR, which was a tokamak in Princeton. And all the experiments that we are running now in this precise moment use deuterium as fuel. It's basically a pure deuterium or pure hydrogen plasma. And the reason is that we wanted to avoid all the pain in the neck, which is the use of tritium. Of course, tritium is radioactive. It's not a terrible radioactivity. It's a short-lived, and it's easy to screen, but it's an isotope of hydrogen, so it's extremely dangerous because it can, for ingestion or inhalation, basically. So what you have to be really careful is just to have a perfect budget of the tritium, and that's what makes use of tritium extremely difficult, and therefore all the experiments have been using deuterium because it doesn't need all this safety action. Of course, now that we are proceeding, I will mention a number of experiments. We'll start to use tritium. This will become a significant issue, by the way, because again, I won't have time to comment about this, but the fact that tritium has such a short life, 12.6 years, means that it's a very volatile item, literally, in the sense that if you buy it today, in 12 years, you have half of that. Future fusion reactor will require a lot of tritium. And of course, once they will work, they will self-breed tritium in itself, but you have to start the process. And you need really tens of kilograms, which, again, I'm not an expert, but I think it's really at the margin, if not, I mean, maybe you know better than me, much farther than what we have available at the moment, because there are not really many ways to produce tritium outside a fusion reactor. Well, let's now move to the future. Of course, with JET, just to be again fair, since you know I don't want to keep you here for hours, and you wouldn't stay here anyway. I just use JET as a sort of placeholder for all, for a number of experiments that have been operating in Europe and outside Europe and are operating during these years. I mentioned you also RFX that is operating in Padova. We had a tokamak in Frascati, so and in a number of other places in Europe and in the US, in China, everywhere. Anyway, the next step after JET is ITER, which is, as you see, an experiment which has, these are cutaways, you know, just slices of the torus, which is very similar in shape, but larger. That's an example of what ITER looks like. Again, here I think we can definitely see a person, which is here. So all this size is around about 30 meters. So we are really talking about a large project. The goal of ITER is to demonstrate the feasibility of nuclear fusion as a source of energy. It's a thermal, ITER has a thermal output. It won't produce electricity. I mean, it's just thermal, neutrons, basically. But it's designed to address a large number of challenges that you will need to solve before building a reactor. In this respect, ITER, it's a very ambitious experiment. On the other hand, it's a very difficult experiment to realize. And on top of the technical issues, when they started it many years ago, this is of course a private opinion, they probably had also some bureaucratical issues. You know, one for all that always struck me is that, you know, ITER, that's a aerial view, which is not even very recent, so much more is built at the moment. But as you can see from the flag, ITER, it's a joint venture between the US, Russia, Europe, India, Korea, Japan, and China. So really 7 big and very different partners. It's probably at the moment, together with the International Space Station, the only enterprise where Russia works together with the Western country, with China. But clearly, the idea of launching this project made of ITER itself a gigantic diplomatic project exercise. And I said the things that, for example, struck me is that you have the vessel. It's built. The vessel is the core of the experiment. It's something which is probably 12, 14 meter high, the donut, and which has to be welded, is made in sector, and this sector have to be welded with sub-millimeter precision. Well, they decided to build them in different locations. So some of the sectors were built in Italy, some in the sector were built in Korea, and it's already I suppose, I'm not an engineer, difficult to be precise if you build everything in a single place. Suppose that you start to build around the world. But anyway, having said that, it's also fair to say that ITER is now not working as an experiment. Its construction is proceeding. It's working now properly, the construction. The director, by the way, is an Italian. He's bringing everything on track. Clearly, it's an ambitious project. It's an ambitious project, and therefore, with respect, as I will comment about this, to other private approaches, ITER has to solve more problems. And in fact, one of the points that I say now is that some of the claims that are made by private companies about the fact that they can be quicker, in my opinion, neglect the fact that some of the problems need to be solved. And you can, of course, design the first car even without the steering wheel, and you can start it, you can go straight, but at some point you have to curve, and so you have to design the steering wheel. ITER is really trying to design everything together, and this is a big plus. This picture that, by the way, ITER has been built in France, near Marseille, and this picture brings us much closer in Padova. This is an aerial view of the Padova lab at the Consortia RFX, and you can see here this white building down here. It's the largest ITER laboratory outside ITER itself. Here it's going to be built one of the system that is going to eat the ITER plasma. Why is this needed? Because basically the whole idea is that once you ignite a plasma, so when you start the fusion, you bring it in fusion condition, then it self-sustains itself. So it produces thermal energy, you convert it into electricity, and then you get electricity enough to keep the plasma going, and also, of course, to deliver to the net. The point is that you have to reach this condition, and these conditions are basically reached when you bring together in a very narrow range the density of the plasma, the temperature, and the confinement time. So interesting enough, each of these parameters, the fusion condition has been reached for each of these parameters, but it's very difficult to reach them together. And this is what makes, again, fusion safe and difficult. That's it's not really a philosophical, but it's really a technical consideration that fusion, we used to say that it's inherently safe, which is true, of course, with respect to, a fission power plant needs less and less with the new design, but still needs active control, human action in case of a runaway condition. And we have seen that all the big accidents happen just because you lose human control, and therefore you are in critical condition and the process can self-sustain itself. A fusion reactor, works in a totally different condition. It really works only if it is within a very narrow margin of optimal condition. If you just are a little bit far away from this condition, the process self-extinguishes. This is the example that I usually do when I go in the school or in the general public. It's just with a cigarette lighter. You keep it switch on in your hand. If it falls from your hand, you have an accident, it immediately self-extinguishes. The same will happen for a fusion reactor. And this means and this is at the basis both of its safety, but also of the difficulty to reach and to maintain this condition. And as I said, one of the conditions is to keep the plasma pretty hot. And you do it in three ways, three, yes. One which is marginal, it's just with a Joule effect. You circulate a current. Or with electromagnetic waves that you launch into the plasma and they resonate with the particles inside and they transfer energy, or with beam. And I'm talking to a community that is very expert in beam, and not by chance. In fact, that INFN, it's a partner of the construction of the negative ion beam, which is being built in Padova. I mentioned you that in Padova we have this big laboratory, which will be the prototype of the beam used in ITER. It's in terms of energy, probably is not to a community which is used to LHC, saying that the accelerator it's as 1 megavolt is not really very impressive. But what is really impressive is the current is 16 ampere. So in total will be a 16 megawatt of energy delivered to the plasma, and therefore it's a pretty significant challenge. I'm not at all an expert in that, but Marco, who has been heavily involved in that, and the INFN community knows that dealing with 16 ampere of beam and with high voltages is not very simple. Anyway, this is proceeding pretty quickly. We do have, that's how it will appear. That's the accelerator with the calorimeter, the residual ion down neutralizer, the beam source here, the pumps. It's under construction. We have a prototype already working of the source, which is called Spider, which is being used. And it's been tested in Padova exactly in these times. So in Padova, in Italy, we have a pretty strong community in fusion. I will come back to that. But first, as I was talking about future, I mentioned ITER. I like to mention Spark, which is another interesting experiment. It's interesting in a number of respects. Also because it has a pretty strong connection with our country and with the INFN high energy physics community. This is going to be a tokamak. Size is not gigantic. These are around about 3 to 4 meters. So you would call it a medium-sized tokamak. But it's going to use a very high field, and it's going to use deuterium and tritium. So it's designed to produce fusion, to convert fusion energy, and is designed to use heavily high temperature superconductor. Actually, one of the main challenges for this experiment is to produce all the coils of the solenoid around the plasma made with high temperature superconductor. This is done by the Commonwealth Fusion System, which is a private company. It's a spin out of the MIT in Massachusetts, and a big player, big partner of this shareholder of this experiment is Eni, the Italian-based energy company, which is involved in the last years as a growing involvement in fusion. The outcome of this experiment will be extremely important, I suppose, also for your community. I heard I heard you explaining me about your seminar. I wasn't here yesterday, about one of the next proposal for the high energy community, which is heavily relying on high temperature superconductor. In this respect, clearly fusion is at the forefront of the research. As you see, the idea is just to have a 12 Tesla, the 12 Tesla magnetic field, with a relatively modest current of around about 8 megampere. And as you see, the major radius from here to here is 1.85 meters. So all this is around about 4 meters. It's really a very compact device. And the use of high toroidal field allows to make it compact. Of course, it's very challenging. I'm not an electrical engineering, but anyone who works as an engineer knows that concentrating this magnetic energy in such a small space, it's really demanding. It's under construction. They promise to have it running really in a few years. If I remember well, it should be within this decade, 29, if I remember well, maybe even less. So it's really, it will be really an interesting project. Okay, I want to move toward the more or less the final part of my talk, and where I anticipate I will talk about the DTT, as Marco has said, and I will make some final consideration. I go back a little bit to the challenges. Why we do all these experiments? Which are the main open problems? First of all, the optimization of the plasma confinement. As I said, in high density condition, there is a lot of free energy involved, and therefore stability control, and the management of intense heat and particle loads at the plasma edge. I will come back to this in a minute, but basically just to give you a feeling of what I mean as non-ideal condition, those that you experience every day in the experiment that you will experience in reactor. If you solve the MHD equation, it's a Newton law, very simple, and you get this very nice nested magnetic surface. That's what you find in the textbooks. But if you look at the real experiment, you do have magnetic perturbation, you do have fluctuation in the magnetic field that eventually lead to stochastic region and to loss of performance. All these kind of things need to be addressed. But there is one which is at the moment it's considered a showstopper, and which sort of inform the physics that we are dealing in the DTT. I try to be, how to say, simple about that, but a fusion reactor will be a gigantic energy converter. You get nuclear binding energy converting into heat. Well, first kinetic energy and finally heat. This energy is brought out by neutrons and alpha particles. Suppose that for neutrons you have a solution. Neutrons have at least one good property. They are isotropic, so they spread energy all around. And suppose that you have a solution to stop the neutrons and to convert the energy into electricity. But the alpha particles, it's less how to say, trivial, assuming that neutrons are trivial, of course, because this plasma as a continuous, you inject energy and there is an outflow of energy, partly used for producing electricity, but partly it's a waste, and you have to dispose of this energy. If you want to have the analogy, it's the same things that the radiator in your car does. Part of energy of the fuel is converting useful energy, kinetic energy that moves the wheels. But part of the energy in the gasoline is converted into heat. And you need the diverter to dissipate this heat. Well, a fusion reactor needs a sort of radiator to dissipate heat. And what is interesting is that this heat goes out mostly as particle, which are then channeled in a pretty narrow channel, which is, I sketch it in yellow, at the edge of the plasma. The way the magnetic geometry is done is that they come out everywhere, they arrive in this channel, and then they are directed down here to this region, which is the sort of sewage of the fusion reactor. It's called the diverter. And they are then channeled towards this plate and pumped away. The real problem is that, this is a sketch of ITER. So from here to here are about 12 meters. It's a big surface. But this channel that we conventionally indicate with lambda Q has a rather small size that has been studied. Of course, it's an extrapolation because we still don't have a first principle model to predict what will happen to future experiments, but we have a reasonable concern that these numbers for ITER and for fusion reactor will be in the order of a millimeter or so. This is really small numbers because, again, consider that this is around 12 meters and this surface is the size of a hand. This gigantic chamber, like this room probably, and all the heat, it goes in a very narrow channel. Which is the things that you can immediately get. The outside surface of ITER is around about 1,000 square meter, order of magnitude. Being so small, this channel, the effective surface where all the energy is conveyed it's of the order 1 to 2 square meters. So you have more or less a factor of 1,000 of concentration of the energy, which means a factor of 1,000 increase of the energy flux. It might seem a bit abstract, but all of you very likely had an experience when you had kids of this very same process and more or less the same numbers. If you have a standard magnifying glass, you can convert the sun energy that would bring you a nice suntan on the beach of Genova into something that can burn things. And by the way, if I'm not mistaken, the conversion factor is more or less a factor of 1,000. That's what a standard glass magnifying lens does. So at the edge of a tokamak, we had exactly this process, and we have to find clever way to dispose about this. One of the way we are exploring is through this experiment, and I come to present DTT, which is the Diverto Tokamak Test Facility, which is under construction in the Enea Frascati side. It's a public-private enterprise. It's the first of its kind as a public-private enterprise, because you see there are the major stakeholder is Enea, which has the 70% of the shares of the society, but then we have 25% of the shares which are controlled by Eni. So there is a significant private interest into that, and a number of institutions, including INFN, which is collaborating. This is going to be a bit larger than Spark, that experiment I showed you before. Here are the sizes. It's using conventional superconductor and the deuterium, again for the same reason that building a tritium plant in the heart of Rome wouldn't be a piece of cake. And what is rather interesting is that even if, for good reason of course, the geometrical size are clearly smaller than ITER and the future reactors demo, these numbers here in red, and in particular this P over R, which is the ratio between the power into the plasma and the major radius, which I don't go into the details, but believe me, it's a figure of merit about the intensity of the heat disposal challenge. It's, as you see, very similar to that of ITER, to that of demo, which means that even if it is smaller, but the concentration factor, let's put, of the heat to be disposed by DTT, it's very similar to that we will expect in future reactors. So it's extremely relevant, and these numbers can be as high as hundreds of megawatt per square meters, which again might not mean anything to some of you, but it's the same order of magnitude of the heat flux at the surface of the sun. So it's a gigantic number which cannot be disposed by standard tools, but needs clever ways to do it, like for example, playing with the magnetic field, designing different divertor geometries, using various materials, and that's what is exactly what DTT is doing, or will do once it will be built. The slide I just went quick was about the kind of parameters we do expect in DTT, which again are very relevant for a fusion experiment. We just published this year the first release of the DTT tokamak research plan, which has been done together with by a community of around about 100 more or less scientists coming from all Europe that have been working together for about a year to produce what is considered the first release of the research plan of DTT, which is basically sort of the index of our research in future years. This is a document that is going to evolve, of course, until we will start operation, and we are probably soon restarting the process for the second edition, should some of you be interested in, of course, through INFN as participating into this effort, but should some of you interested in joining this, you are more than welcome. I conclude with, I need 3 to 4 more minutes, but to open what I think is a totally new area of investigation. which is the following. And I start in this case from my personal experience. I'm in this field from many years, too many probably, but as almost everyone that has been in the field, you know, from a long time, I know that I started my career into fusion with the narrative that fusion was energy from water and infinite and going to solve the energy problem of the mankind, very simply speaking. And this is not only because, you know, in Italy, this was, you know, I worked in the UK when I started, and I worked for many years in Germany, and this was the story, I mean, basically, you know, and I suppose that if you were kids and you looked, you know, books, they talk about this. And up to now, fusion has been considered a scientific or technical challenge. But in the last couple of years, I personally realized that since we realized that the fusion it's coming closer, conversation about non-technical issues associated with this source are important also in terms of social and ethical implication. Because it's clearly that there are 2 points. First of all, fusion is going to influence, if it works, it's going to influence significantly the mankind. How it's going to influence is something which is in our hand and is not absolutely clear that it's going to be the infinite amount of energy for everyone that I was talking about. There is also, since, as I gave you the example, in the news now fusion is coming pretty high, it's coming under the scrutiny of the public opinion. So we have to be prepared to be transparent and to be very clear about what we are doing. Again, this would deserve an entire talk. Actually, this is a part of what I'm doing at the Centro Interdisciplinare of the Accademia dei Lincei. But I just want to give you a couple of examples, just to 3 actually, very quick. First, this is the map that represents the electricity distribution in the world. As you see, all the dark regions are mostly in Africa, where around about 800 million people don't have access to electricity. The narrative of fusion was that we are going to give electricity for free to everyone. I'm exaggerating, of course, but this is the story. If you compare it with the map of the distribution of laboratories or companies working on fusion, you can see that they are rather complementary. You know, it's not straightforward that countries that desperately need electricity would benefit from fusion. I mean, it's not a direct implication. It could be, we hope it will be, but you need some work. So this was the first example I wanted to make. We do have a problem, in my opinion, of communication and connection with the society. After all, you know, I think that you heard in Rome, the ITER Director General says clearly that ITER has been paid by taxpayer. It's going to be open source. It's going to be open to everyone, and so we all grew and we all belong to a community where access to data it's open. You know, we were just discussing also this morning. I'm not an expert in the field, but I suppose that if I have a super brilliant idea and I follow the right channel, I can have access to LHC data and maybe got a Nobel Prize. You know, that my country paid for that, and you know I can access. This is not going to be, again, necessarily the case for fusion once it will be, if it will be completely controlled by private companies, because private companies do it for money. And of course, this is something that we have to take into account. In addition, there is a significant point about communication. This is a pretty interesting poll that has been done again by the Fusion Industry Association. It's the association that keeps together the 47 companies that joined it, and are the major companies that are working on fusion. They publish every year a very interesting report. This is publicly available. And this year they asked the question to their members, when do you anticipate your company will deliver power to the grid, all right? Power to the grid. Not will make fusion, will make an experiment, will ignite tritium, power to the grid, here. You know, I think it doesn't need really comments. You know, I'm a super fan, you know, I'm based, you know, I worked all my life on fusion. I would be happy to see fusion. By 2035, it will be very close to my retirement. Actually, 2035, I will be retired. I would be happy to see fusion. I'm a bit doubtful, but anyway, I don't really want to comment because it's their work. They are responsible for that, but it's clear that it's providing a message, because put together this with the declaration that has been made last week at the G7 where Marco was, and today at the COP28 where fusion, you put together this. You know, I have a lot of close friends who are journalists. You cannot blame journalists if they put them together, if they made a short circuit. And clearly, you know, it's on the other end, then public research, Piero and the ITER Director General, Eurofusion, we are much more prudent, but clearly there is an issue of communication. And then the final point that I conclude, which is I pick it just by as an example, because we all know that is not a real issue, but it's very often towards the public opinion, doesn't matter that it's a real issue, it may become an issue even if it's not. And which is the risk of proliferation, sorry. A fusion reactor, it's a very intense source of fast neutrons. In principle, of course, you will use these neutrons to, as I said at the beginning, to breed tritium out of lithium. But you know, in principle, you could misuse these neutrons to enrich uranium or thorium and to build nuclear fuel. Our community in the past has made analysis on that. And the very simple answer is that you know, we shouldn't be really concerned because it's too complicated. If you are a terrorist, or if you are a state that wants to start the Third World War, you don't need to build a fusion reactor to produce nuclear fuel and weapon graded fuel. Sorry, and we know that around the world, you know, centrifuges are much cheaper, much more effective, and you don't need to build ITER to do this, no? But on the other end, it's there. So we have to be very open about this and to tell that, to explain. I just picked this example to say that communication and ethical problems of interaction with the communities are really very relevant. And this is my last slide. We had at this school, at the Venice International University, this summer, I put together a number of people, and I was pretty pleased because the Venice International University is a consortium of around about 30 universities from around the world, and every year there is a call for application. They finance 3 of these PhD schools, and our proposal was accepted, and it was really very, very interesting because I put together physicists, engineers, anthropologists, social science people, and we really tried to discuss this in detail, and I hope that the discussion, the conversation will continue more and more. Anyway, I abuse of your patience. Thanks a lot, and well, I'm open to questions.
Thank you very much for the very interesting talk. Questions or comments?
We agreed with Marco that we can be very nasty in the question and in the answer because we canceled from the recording then. So,
so I'm not going to ask you anything technical. I am an LAC guy, so I know small beams and not much energy involved. So speaking of timelines, I am a guy of a generation, more or less yours, that we were told that fusion was the real energy for next century, something like that. Are things changed in last years so that we can say that it may be something? So that, I mean, you showed that that poll. So that the first energy, electrical energy delivered to the grid can be this century, in this century, and not in the next one, or never.
Yeah. Well, thanks. It's an interesting point. In fact, I think that we all agree we don't want to comment that poll. I mean, it's there, and it was just for information. It's public. But about the timeline, it's a very interesting the point you made. I would start from. I would answer with 2 points. I think that I hope we all agree that if you look at any energy transition scenario, renewable will be a big player, but you need a fraction of nuclear energy. I mean, that's for the base load for a number of reasons. I'm not a super expert about that, but we need it. We have fission, of course, but my feeling is that in the long term we need fusion. So I don't think it's a matter of it will come or never. I think we really need to find a way. Times. Well, this is I think, and even the more realistic and prudent estimates claim that in the second half of this century we will get fusion, and I think they are realistic for a number of reasons. We have a lot of research has been accumulated in the last decades, and this is now synergistic with the big effort from the private companies. Of course, some of these efforts are, let's say, risky, but some of them, like the one by Spark, are extremely solid. So they are really working on a concept which is very solid. And of course, they have an attitude which is different, for good reason, from that of public research. They can afford risk. That ITER cannot afford risk. It's too big, it's too expensive to afford risk, and also it's also aiming at solve a large number of problems. Spark has a very narrow focus, and so it can take risk. They have a lot of venture capital, so they have money, and they can do what I used to say to give this example. If you go into the internet, you will find EBR-1, which is the first civil reactor in fission, which was operated in 1951, just 9 years after the Fermi pile, the Chicago pile, in Idaho. And it's interesting because from these big things, just 2 wires came out, and they light 4 light bulbs. I think that the electric output was 500 watts, something like that, tiny. But it's in the history books. It was the first time that you used fission energy to produce electricity. I think that fusion needs it. This can come relatively quick, but then more time will be needed to solve all the other problems. And this is why I think that the timeline of ITER is absolutely consistent with the timeline of the aggressive companies, because they may show that it works, but then you have to solve problems that ITER or DTT are solving. So just to make a long story short, my feeling is that, yes, that the second half of this decade, it's very reasonable. I would probably not have voted for the next 10 years, that I'm pretty sure, if I had to vote.
Okay, thank you. I have a question about the involvement of these private companies, because I expect this to be some sort of strategic industry in the future, like silicon industries now. And now we have very few companies in silicon industry that are able to deliver their products, and mainly because of a patent system that clogs basically all the market and keeps newcomers outside. So are there already issues related to patents in fusion technology that may pose these, there can be a challenges for actually the widespread adoption of this energy source in the future?
I think you pointed to the right problem. It's exactly the reason why I started to address this, the final point of my conversation, because this is something we have to be, that is going to be an issue, yes, for sure. I mean, all these are private company. They're owned by investors, and their major engine is money, is business. I mean, it's totally, it's crystal clear, it's profit. And yes, we should exactly expect something like that, that some of the things will be patented and they will not be freely accessible. There is I'm rather open about that because it's an open literature on physics of plasmas. Last year, they published an issue dedicated to private companies in fusion. And it's pretty interesting that I think it was probably the Spark group that they presented their experiment, and in the paper, it's a peer review paper. The last two sections were dealing with data access in Spark. How will data access in Spark will be organized? And it's a very interesting reading because it's very different from the way, as I mentioned, we are used now. And so, yeah, I think we should expect this point. And we should find a way, if one, to address them. But clearly, for example, if you take that document that I showed before, the US strategy on this is to have a very strong partnership with private companies. So they are going to be big players. It's pretty clear that, in my opinion, that some of them will not survive for long because probably their concept won't be winning. But some of them, yes, I think that will be a big player.
Thank you for this talk. So I saw a talk about 2 years ago that said something like, if fusion was discovered right now and shown to be working, then it would take until something like 2050, 2060 for it to be economically viable. I don't know if you've addressed this a little bit, but I don't know if you've any further comments on this, or if you think this window has shortened and is shortening every year, for example.
Well, I think that there are, to be frank, there are different opinions in the community about that. I give you my private opinion, and my personal opinion is that this window that you mentioned and that he also mentioned, which is the second half of the year, it's reasonable. I mean, it's I expect acceleration in some specific topics. Take, for example, high temperature superconductors. It's clearly that the push that fusion has given to this is very strong, and this could benefit other fields like energy physics. But in terms of delivery of efficient and economically viable power, my opinion is that yes, we need time.
Hi, thank you again for the talk. It was very nice. And my question is about the fuel. Right now we are depending a lot on oil and gas, and so on other countries. Then for fission we would again be dependent on uranium. And what about fusion? Like you said that for self-breeding the tritium we would need lithium, but that is very important also for batteries. And in Europe we don't have much lithium.
Yeah, right. You know, one of the two fuels of fusion, or magnetic fusion, which is deuterium, it's rather easy, of course, to be obtained. Tritium is more delicate. You correctly remember that it's breeded by lithium. And it's definitely going to be not a straightforward issue in its thinking. I think there are ideas on how to do it. We haven't done it yet on such a large scale, but it's clear that on one end, we should remember that it's clearly a nuclear process, so the amplification factor is large. So you don't need so much lithium as for batteries, I mean, for a reactor. So even because, don't forget that it's totally out of my field, but up to now we are not recycling lithium simply because it's cheaper to mine the new one for the batteries, for example. Excuse me. Simply because there are not, it's not economically viable. But as soon as becoming viable, which means as soon as more vehicles are on the road which have lithium battery, it's predicted that it will be recycled at a very high level, as we do it now with the lead batteries. And lead is much cheaper than lithium, but still we recycle it because there are so many cars around the world that it's economically convenient. So I don't expect it will be a huge problem, but certainly we need a technology that has to be developed. I mean, we have never done it before, so. About the availability, again, we go back to the other problem. Geographical availability, again, technology, patents, and same story.
So I would like to ask something different. Thank you for everything now. As far as I understand, the approach from ITER and demo, and the approach from, as an example, the Commonwealth fusion companies and so on, is very different. I mean, on one side, you get larger and larger reactors to get the breakout, the break-even, and so on. On the other hand, they point on smaller reactors and faster development and so on. If you are a very rich investor, where would you put your money?
You have the answer, in fact. The point, because it's exactly what you said. You know, ITER is large, you know, for a number of reasons, but because it used a lower magnetic field, and also because it wanted to address, as he said, in a safe way, all the issues that you can expect in a reactor. Spark has decided to go quick and small, and with a very precise focus. But again, in my personal opinion, Spark will need, I mean, the line that goes with a small, with high field, a small reactor, sooner or later, before being translated into an electricity plant, will be the solution, will need the solution of the heat flux issue. And this solution can come only by ITER or ITER class device, and DTT will definitely give a significant contribution to that. We as scientists know it. Then you ask me, right, if you were an investor, well, the question is, it's clear. The investors are putting money on the things that appears to be short. It's their money. It's clear that there is a risk that it could be a bubble, and it's there. The risk is there, obviously, but sorry. That's the economy. Yeah, right. You know, I personally would not put my money on some of these concepts that we can discuss at the coffee if you had, if you have some free money and you want, I can give you some recommendation, but. Anyway.
Thank you for the talk. As what I know, now in Italy we can't produce nuclear energy.
Sorry, now?
By law we can't produce nuclear energy, as I know. Does it affect the research that we do here in Italy, or what we can do to the nationwide resources?
No, maybe Marco can comment better than me. Certainly from a legal point of view, there is no limitation in research in the country. No, certainly not in fusion. I cannot talk into details about fission if it has been limited in some way, but basically not. Of course, clearly when after the first Chernobyl and then Fukushima, with the shutdown of the nuclear fission program in Italy, clearly these affected investments, obviously, and industry, and so money into the field, but no, research has not been affected, certainly not in fusion.
Okay, so I think we should probably close the question and answer session here because we have a department meeting at 3. But there is coffee and refreshment outside, and I'm sure Piero will be happy to chat with people. Just a reminder, the final colloquium of the year will be in December. Now I don't remember the date, but I think it's mid-December, always on a Wednesday, and it will be back to fundamental science. It will be particle physics and machine learning. So see you next month. Thank you.
Grazie.